So last period, we talked about several factors that will affect reaction rate, and here is just a quick refreshment. So I hope if you guys do not remember what happened last class, this will be a great opportunity to review. So several factors that may affect reaction rate, the most important being concentration. And then you can think about, okay, well, generally reaction become faster at higher temperature, right? Because molecule will collide into each other more frequently. So temperature is the other very important factor. And in later semester of the semester, you will see there's a lot of equation. It has a temperature term in it. And then, as I mentioned, at higher temperature, the frequency of collision could be higher, and also the energy of the collision will be higher. And finally, catalyst will briefly touch on this topic near the end of this period. So what is a rate law? So you have to remember, rate law is to describe the relationship. It's a mathematical expression that correlates reactant concentration with your reaction rate. So the rate is how fast your product is forming or how fast your reactant is disappearing. So you have to remember that. And also, I would like to point your attention to table 16.3 if you do not have your book. So simply make a note in your note and check out that 16.3. I do not want you to memorize that table, but simply recognize the unit, and that will tell you the order of a reaction. And then we also talk about how you can fit the reaction data and then figure out what's the order of reaction, right? It's a very simple mathematical calculation. And I want you guys to remember the overall reaction order would be the sum of all the exponent of your equation, okay? That's very simple. All right, so now we'll have a quiz. I would like you to write down how would you express the rate of the disappearance of the SO2, disappearance of oxygen, and as well as the formation of SO3 based on the number given here. You can use your cell phone for a calculation if needed, okay? It's a very simple calculation. Or you can just leave your mathematical equation. How would you express the rate? How would you list out, how would you use these numbers to calculate how fast each reagent is disappearing and how fast your product is forming in this reaction? Okay, so are you guys almost done? So now we'll move on to the class activity for this period, okay? So I plan to finish this chapter. In the last period, I mentioned reaction order must be determined by experiment, okay? And I did not have a lot of example, but today I bring a lot of example of a lot of common equations, okay? You don't have to copy down this slide. You guys will receive a copy of slide at the end of this period, okay? But these are likely to be the problems, equations I will create exam questions on, okay? These are reactions you probably won't do ever in your life, okay? But these are very important gas-phase reactions. So in the early days, a lot of physical chemists will do these reactions and figure out reaction kinetics and reaction thermodynamics based on these reactions. Okay, so I want to point out the exponent, the factor in front of your reagent would not necessarily translate to the exponent in your final rate law. But in some cases, see, it's possible to have exponent as a fraction, okay? So it really depends on the reaction mechanism, and we'll talk about it later on. Okay, so here is a general graph table, and you can see this number that doesn't really have a correlation for your final rate law, okay? But when you write a rate law, it's always you have a small k, okay? Do not write big K, small k, and for your reagent, okay? So in case of that, it's a zero order reaction, which means it does not depend on your reagent concentration, you can cross out the term. Okay, so we will come back to integrated rate law later on because I need to use a blackboard. But first, I would like to cover Arrhenius equation, which is the fundamental equation that would describe chemical reaction. Okay, so a little bit background, Arrhenius, okay? He's a Sweden physicist, but he's also regarded as a chemist. So back in the day, probably like 100 years ago, the line is not very strict between physicists and chemists. Okay, so why I bring out this map? Okay, this is just put into perspective where Sweden is. Sweden is radiant. Okay, so we probably already heard about global warming, right? And now it's being rephrased to climate change, and it's a very serious issue. And in fact, Arrhenius used a bunch of equations and the concept in physical chemistry to prove that increasing CO2 concentration is related to Earth's increasing surface temperature. So this climate change or global warming news is not new at all, okay? Back like more than 100 years ago, this guy already proposed, okay, the potential correlation between the CO2 and how that would raise the Earth's temperature. Okay, so that's significant, okay? And later on, we'll learn about electrochemistry, right? We'll learn about acid and bases, right? When he was pursuing his PhD in Sweden, his PhD worked on conductivity of electrolytes. Okay, so however, back in the day, nobody believed his theories. Okay, and then it was proved after he graduated. Even his own advisor did not approve his theory of conductivity of electrolyte. But later on, everybody accept. Okay, well, when you dissolve salt into solution, okay, they dissociate into paired charged particles, so that's later known as ions. Okay, so now you know why I want to bring up this person. I mean, he is a founding father of physical chemistry, right? Without this realization, we cannot, like this book could not be possible. All right, so later on, he talked about, okay, what is acid, what is base? Okay, so back in the days, you guys probably just memorized, okay, what is acid? Okay, it produces hydronium, right? And then what's base? It produces hydroxide, okay? But before people have these concepts, he was the first one that actually proposed such concept. Okay, so in 1889, he coined the concept of activation energy. So this is the most important. So there's a lot of definitions in this part, general chemistry, okay? So I want you guys to memorize this. So what is activation energy? There's a lot of correlation you will see again and again in the semester. So activation energy is a correlation, the relationship is a correlation between reaction rate and temperature. Okay, so there are several persons I want to mention. Okay, so does any of you recognize any of these names? You guys should recognize Mendeleev, right? Mendeleev, he created periodic table. And this past year is a periodic table year, okay? Do you remember the Russian chemist, okay? He put all these elements back in the days. He was around, there were only 56 elements, okay? He put them into order and predict that we can make some of these elements down there, okay? And he was a 1906 Nobel Prize winner for chemistry, okay? And this guy, he got a Nobel Prize in 1903, okay? So who is Nernst? So if you guys remember electrochemistry, there's an equation that talk about how this is related to the electropotential, how fast the electrochemical reaction could happen. A very important person that figured out the mathematical expression for third law of thermodynamics. So we'll talk about thermodynamics later on. So he was the one that did third law, okay? But you don't have to remember he created the third law, but you have to recognize, okay, he is involved in basic principle of thermodynamics. And also propose atomic chain reaction. Later on, we will have a chapter on nuclear chemistry. Okay, so atomic chain reaction theory is related to nuclear fission. Okay, so I would expect you guys to know the difference between fission and fusion. Okay, two very important nuclear processes. This Clausius, we already saw his equation earlier, right? So you should check out your page 480. There is a Clausius-Clapeyron equation. You have to recognize these names. Okay, so because these are very important equations that, for example, this Clausius-Clapeyron equation that I mentioned related different pressure to the temperature, and by using heat of vaporization as a constant. And also we talk about kinetic theory of gases, right? We can figure it out root mean square speed of gas, and it varies based on its mass, right? This guy figured out the equation, okay? He's very important. And more importantly, I know a lot of you did not recognize the word entropy on the concept exam, right? This guy come up with the term entropy. Okay, I just want you to remember one word. Entropy means randomness, means disorder. We'll come back to this concept later on. And more importantly, he come up with the second law of thermodynamics. So you can recognize that back in early 1900, there's a lot of very important scientists that come up with these terms that's now in our textbook. All right, so what about Ostwald? How could he be related to our textbook? Okay, so he created Ostwald process. We'll briefly mention it in the catalysis section. So he process is an industrial way to make nitric acid. Without nitric acid, we would not have explosive, we would not have fertilizers, we would not be able to do your acid-base chemistry. And also, for when we talk about reaction rate, we generally use mole per liter as our unit, right? Everybody on the same page? Mole per liter? Okay, Avogadro's number related to mole to number of atoms, right? Who come up with the mole? Actually, Ostwald did, okay? He simplified these numbers, otherwise we'll be dealing with a bunch of random numbers with a factor of 10 to the 23. All right, so Van Hoff, he is involving a lot of chemical equilibrium and kinetics, as well as thermodynamics, okay, and also a Nobel Prize winner. So that's why I want to highlight these people. I mean, they are very important for how chemistry knowledge is structured nowadays. Okay, let's go back to the Arrhenius equation. So this is what the Arrhenius equation looked like. Okay, so he basically did the reaction, measured the rate constant at each temperature, and that he did not observe a linear plot. Okay, so the best way to fit this data is to use this exponential math function. Okay, so this is what this equation generally look like. So you may wonder what A is, right? Does anybody know what A stands for? I'm glad you guys have something new to learn today. So activation energy, okay? What is activation energy? It relates the rate constant to different temperature, okay? This R is a constant, okay? A likely to be a constant, and it's a constant that it describes the frequency factor. So that means the orientation, how the molecule hit each other, and also the collision frequency. Okay, so it's a constant over here. So it ties multiple things together, and then we have to recognize that when we have a chemical system, not all the molecules move at the same speed. Some move faster than the other, and it gains this momentum or energy from the surrounding, and then so the temperature is a factor that dictates how fast they will move. And then when they move fast enough, we have recognized all these particles have a distribution of energy, and only the ones that move fast enough and collide with another molecule at the right space, chemical reaction could happen. Okay, so activation energy is an energy barrier that we must overcome before your reaction could happen. And this is what a typical plot would look like. This would be what's so-called activation energy. Okay, we have to overcome this barrier before you can get to the product. So I want to point out here, in these equations, generally the unit for temperature is not degrees Celsius, it's Kelvin. Okay, so anybody want to tell me how you relate Kelvin to Celsius? So it's just a simple constant that you add on to the Kelvin temperature, okay? So the absolute number is 273 and something decimal, but it's not important, okay? But you have to remember when you're doing calculation related to activation energy, you will have to use Kelvin. Do not use degrees Celsius unless you have the right unit, okay? In this reaction, the energy level decreases, right? So your product is lower than your reactant, okay? We know chemical reaction, we break bonds and we form bonds, okay? What happened to the extra energy? The extra energy will be either released, or if it's missing some energy, it will absorb such energy for the reaction to occur, okay? So the very important concept here is that when you see your product energy level is lower than your reagent, it's an exothermic process. So that means release heat, okay? When you see exotherm, that means the amount of heat being released. So contradictory word to this, okay, the opposite of exothermic reaction would be endothermic. And this means internal, okay? And this is the opposite of internal, so you have to remember, you just have to memorize this. Endothermic means it's absorbing heat from the surrounding. Exothermic means you're releasing heat to the surrounding. So when we're talking about chemical reaction, we're talking about our system, okay? So there's a system, your chemical reaction, and surrounding, okay? So how would you get this heat of reaction? Okay, so if we look at this plot, in order for the reaction to occur, you must overcome this energy barrier, right? So this energy barrier is your forward energy, okay? And then the energy level from your product to this activation energy is your reverse. So for a reaction to go backward, you have to overcome this amount of energy, okay? So for the heat of reaction, you simply do a math, activation energy forward minus activation energy of reverse. So it's very, very, very simple. When we see a exothermic reaction, because you're releasing energy to the surrounding, it has a negative sign, okay? So opposite process, that will be a positive sign. Okay, so it really depends on what you're looking at. And now we will care about our chemical reaction system. All right, so how would you obtain activation and energy? If you look at this equation that's already been figured out by Arrhenius. So we can do a simple mathematical process of such equation, right? By taking a natural log of this on both sides. Okay, if you do not understand how this happened, I would suggest go back to your math textbook. It will show you how natural log cancel out with the exponent term, and that is just simple operation. Okay, and by seeing this equation, you recognize that we can do plot. It's very, very simple plot is what's called y equal to mx plus b. Okay, so if we care about this term, what we can do is this could be our y term, this could be our x term, then obviously this a, which is a constant, would be your intercept on your graph. When you plot the data, it should look like this. And then the slope would be your E activation over R, which is the constant. Okay, so you can do multiple reaction like this and figure out your activation and energy. And why does activation energy matters? Why do we care about activation energy? You can think about the magnitude of activation energy, because a lot of chemical reaction will deal with energy, right? So we want to know how much energy we need to put in so that we can figure it out whether this chemical process is a viable way to do this on an economical scale. And also, we can figure it out when we're talking about setting up a reaction, we will have to worry about whether such condition is good for this reaction. It is a spontaneous process, right? If it's not a spontaneous process, that means we have to put energy or remove energy from such system. And we'll cover more of these topics when we're talking about the chemical equilibrium. So in the later of this chapter, there's an important concept of catalysis. And most of you did get that question right on a concept exam. Is in the case of a catalyzed reaction where you have a catalyst that would not be consumed during reaction, but instead it will interact with your reagent and lower your activation energy, and by doing such plot, you can figure it out, okay, how efficient this catalyst is, right? If a very efficient catalyst can lower your energy barrier by a lot, a useless catalyst, an ineffective catalyst could not do so, right? So by running this analysis, you can simply figure it out how efficient your catalyst is. So in another way to look at this is that when you draw a trend line, you're going to have a lot of point on it, right? And since activation energy is a constant, you can pick any of these 2 points and determine the slope, and that will also give you the activation energy. So that leads to a very important equation. So this is something you guys have to able to do on your exam, to do such calculation without mistake, okay? It's very easy when you type in your calculator and then you make some mistake. If you want, you can rearrange the equation on your own, okay? It may look simple on the paper. If you just look at your textbook, it looks really simple, but I will encourage you to actually write it down, okay? Actually go through the calculation because it's very easy to make a mistake. And you have to recognize you must have T1 over here and T2 over here and K2 over K1. So another important concept in this plot is what you see here, activated complex. Okay, so that is transition state. Okay, transition state means this is the highest energy. This is NO partially bonded to this O3. It's undergoing a very effective collision that will make a reaction happen. So this is related to the concept of activation energy. It has to go over this energy barrier for the reaction to happen. So the activated complex or transition state is at this highest point. And then when you reach to this point, the reaction can go either way, okay? It doesn't mean when you get to this highest energy, it has to go to the product. There's gonna be a reverse rate going backward, okay? So I would encourage you to read page 719 in your textbook when you go home. So make a note, just read that page. Sometimes you may wonder what physical chemists do, right? So physical chemists, they can use very advanced laser technique. These pulse lasers, they can actually detect the chemical bonding, right? So you can actually observe these intermediate, these activated complex, because these things are not very stable, okay? And their lifetime is very short. With conventional analytical technique, you cannot visualize them, okay? So actually in our department, several physical chemistry faculty, they work on these pulse laser technique to observe reaction intermediate. Then you can postulate reaction mechanism, which we will later describe. Now I want to talk about the integrated rate law, okay? So last period we talked about first order, second order, and zero order reaction, right? So I will talk about the first order reaction. Okay, so if you integrate both sides of this equation and rearrange it, because we care about after a certain time what happened to the reagent concentration, right? So this is after a predetermined time, and 0 means the beginning of your reaction time 0. Okay, so in the end, if you do the integral, you will get, and then you recognize a very similar processes to what we already described. Put exponential term, both sides, and then if you times the initial concentration on both sides, then you will get a simple expression that will tell you how much reagent you would have left after a certain amount of time. Okay, and in your book, there's a table that summarizes this, table 16.4. You guys can walk through this practice, and then you can get the solution for different order of reaction, okay? And how would you be able to determine the reaction order based on the data that was given? A simple practice is what I plan to do in this lecture. That's why I want you guys to bring the laptop, because we'll simply fit the data to each of these 0 order, first order, and second order to see whether you can get a linear plot. Okay, so if you guys open your Excel sheet, you will get a time versus concentration data, right? So now we have these solutions, okay? So what you can do is, we know the initial concentration, right? So you can process your data by taking another column next to your concentration, take a natural log of it. And in another column, you can take 1 over your initial concentration and the concentration at each point. So that will give you a new value, right? And then you can simply plot the data the way that is shown below, okay? With respect to time. If you're getting a straight line, that means you are on the right order. Okay, and then the reason why I wanted you guys to do this practice is, if you simply just look at the data, I mean, in some ideal case, like last semester, if we have to keep one reagent concentration the same and look at the rate, then you can figure out a reaction order. But in real life, not all the reaction work this way. So fitting data is an effective way, and I feel like no matter what major you are, you will have to make pretty figures at some point. So I want to mention, it's a skill that you make a good looking graph, okay? So generally, for a graph, you must label your x and y, okay? Whatever your y is, okay? Otherwise, nobody's gonna understand what this is, okay? Second, it's always good to have a title for your graph, okay? What are you looking for, okay? So, or it can be simply correlation of reaction rate to time, okay? Correlation of 1 over concentration, right? And I also will encourage you guys, when you process the data, write down your equation above your column. Otherwise, you're not gonna remember what kind of mathematic processing you did to it. And then, generally, when you present a graph, you want it to be readable, okay? So don't just put in Excel and generate a plot and just hand it in, okay? You have to look at the font, okay? And generally, people will make the line thicker so it looks better. And some people like to actually finish the border for such graph. And generally, this make graph looks more professional. So if you look into chemical literature or physics literature, you will see good looking graph, okay? If you have an ugly Excel, crude, not processed graph, if you submit it to a journal, generally they will send it back to you, okay? So I know you guys are still very early on in your science career, but knowing how to make good graph is an important lesson. So this is why I want you guys to actually try to spend maybe 10 minutes on this exercise. Okay, so this is a practice to show you how we process these data. Okay, so next in that table 16.4, you also saw half-life, right? And you guys probably did not have this concept before, but I'll briefly walk you guys through what is half-life before we move on to the last part of this chapter. The concept of half-life will come up again when we're talking about nuclear reaction. But basically, half-life means your reagent concentration decreased by 50%, by half. That's why it's called half-life. Okay, so what you can do with half-life, for example, in a first order reaction, we know half-life at T1 half, your reagent concentration will be half of that of initial. Okay, so you can simply substitute this into your natural log, okay, or your second order reaction, and that's how people figure out the half-life of a rate law. And this is for someone whose math is not very good. So by looking at the kinetic plot, okay, you can figure out, okay, how much reagent do you have left after three half-life, 4 half-life. So it's a very simple way to figure it out. And then on your concept exam, there's a question like that. Okay, so for first order reaction, if you simply do the math, then you will get half-life is natural log of 2, which is 6 point something, 0.6 something, and over your rate constant. Okay, it's just a simple way to calculate stuff like this. And if you do not understand, I would encourage you to read the textbook. It's a very simple concept. It's simply it describes how much time does it take for your reagent starting material concentration to be half of our original value. All right, so, and then we talk about catalysis briefly, right? And then what would be a zero order reaction? And I want to bring this to your attention. How many of you drink alcohol? Okay, so consumption of ethanol is an example of zero order reaction. Okay, your body will process alcohol and turn it into aldehyde and acid. Okay, so there's some enzyme called alcohol dehydrogenase that will oxidize alcohol. Okay, and then we'll talk more about it when we talk about organic chemistry near the end of the semester. But basically, it utilizes some cofactor, which is another type of basically the fuel for the enzyme to undergoing these chemical reactions. Okay, so this is what the rate will look like over time for alcohol. So this is ethanol concentration. Your reaction rate will remain constant. It doesn't really change based on how much alcohol you consume. This is how fast your body will be able to process alcohol. So only way to become sober is time, okay? Caffeine doesn't work. Some people believe caffeine will work, okay? And it doesn't change. So if you look at the concentration of alcohol, so I call this decomposition or oxidation of ethanol, okay? If we look at the concentration in your body once you consume, because the only way that you can remove this from your system is by oxidizing into other species. This is what the rate law will look like, and you already seen that in the first lecture on the effective reaction order on how fast a reagent decreases. Okay, I think I covered most of what I want to cover, and we'll move on to the most difficult part of this chapter. Okay, so usually when you see a chemical reaction, the expression, right? But in fact, there are a lot of different steps. So when we're doing reaction, a lot of chemists care about reaction mechanism. And then here it's a simple demonstration to show you what is a rate limiting step. So for one simple reaction that you see, it may involve multiple species that form, an intermediate that form during the reaction. Okay, so rate limiting step is what limit how fast your reaction can go. As shown in this figure here, it could be the first step, it could be the second step, or the third step, but we really don't know unless we actually do the experiment to either capture these intermediate or monitor the amount of media being generated and being consumed. And I prepare a little different example. I mean, the book did not really specify this to be steady state approximation, But if you read the book on the relevant pages, page 724 to 725, okay, if you actually read the pages, that will be the literature that's supporting what I will be talking about next. But I did recognize that I did mention molecularity. Okay, so now turn to page 722. So, I mean, that concept is quite simple, molecularity. So if you're A directly becoming the product, it's called unimolecular. Okay, when you see unimolecular, that means only one thing is involving in the reaction. And if you have two molecules collide into each other, forming another molecule, that is called bimolecular. Then in some very rare cases, you will see termolecular. Ter means three. This is very simple. You remember uni, bi, and ter. So now I would like to direct your attention to sample problem 16.10. Is right below the table 16.6, and that is what the reaction mechanism will look like. So you can simply cross out the product and reagent that show up, right? And then give you a simple equation, highlight in green. Then one of these steps, if you were to get the rate constant, you can write rate law for each of these equations. But like I said, sometimes it's very hard to figure out which is rate limiting step. So sometimes we need to make assumption, especially when there's reaction that it has both forward and backward reaction. Okay, so that means when I have a product, usually in a simple way, we say A become B. But in reality, equilibrium is always there, okay? Everything wants to be in the equilibrium. So you will be likely see an expression like this. It's called a reversible reaction. Noting that the arrow here is a half arrow. That means it can go both ways. So do not write this. So let's look at this steady state approximation. So in this reaction, this compound will become nitrogen dioxide and oxygen. And then if we assume the intermediate in this reaction is consumed very quickly as it forms, that means it reached to a steady state. So that means this intermediate INT, what I draw here, it changed with respect to time is 0, okay? As soon as it's formed, it's being consumed, okay? So the process of forming it will be the rate limiting step, okay? So these are the mechanism for such a reaction. So first, there's a forward reaction and backward reaction that give you NO2 and NO3, right? So this is very common. And once the NO3 is formed, it can keep reacting with NO2 to form NO2, and oxygen. But if you look at this final rate law, okay, so it doesn't have NO in it, right? So that means the NO is consumed somehow in such process. So NO3 plus NO become NO2. And if you add these together, then you will get such equation. By doing steady state, so if we're looking at intermediate, it's in your reaction, you will reach a state where, for instance, in this reaction, when you form the NO, it's consumed by the NO3 immediately. So let's get into a group. I want to see a group of 2 and 3. Forget about what I say about steady state for now, but what you're doing is called a steady state approach. The textbook does not say that, but it uses the same principle. So let's write down some rate law for NO, for the production of NO and the consumption of NO. Write it down and compare to your partner, or you can work on it together. Either way is fine. Okay, did most of you get this for the production of NO? Right? So this is quite simple. You should already know this by now from the first lecture. Okay, so if we look at this equation, it's simply saying the production of NO, so it's K2, and then times these two terms, the concentration of these two terms. Consumption of NO is simply this equation, right? This is consumption of NO is this times K3. Then you will use the steady state approach. This is what steady state approach, because I already mentioned, okay, this is not in the final product, right? So it must be consumed somehow during this reaction, right? So it's an intermediate that will have a very short lifetime in your reaction. So based on this rate law, you can solve for, no, actually you can't solve anything yet. But I guess now you're using this method to solve for NO3, okay? So look at how is NO3 being produced, and look at how NO3 is being consumed. This is a little bit trickier because you have to realize this is a reversible process. So for this equation, you will have to have two types of rate law, right? It's being generated and being consumed. So I want you to group the production on the one side and the consumption on the other side, because you have to realize the sign will be different. If we're talking about producing something, the amount is increasing, right? So it's a positive sign. If being removed, being consumed, it's a negative sign. Okay, so let's look at this carefully and write out all the possible terms, expression for NO3. Okay, how many of you get this? I already seen several of you figure it out on your own, so which is quite impressive. For the NO3, right? So there's a backward reaction, and you have to consider these two reactions, right? And then with this equation, you can solve for NO, right? And then you can solve for NO3. That makes sense? So you simply move things around, okay? And eventually, for the final rate law of oxygen, you can come up with this equation. It simply have all the constant without all the intermediate that is present in this equation. So I already gave you the solution, and I would like you guys to walk through the calculation. I mean, moving these terms around should be simple, okay? If you have trouble with it, please let me know, and then we can figure it out how to help you to understand this better. You can look at your textbook, your page 725. It's a simpler version of this. But I hope this difficult problem was just to give you a practice of how to move these terms around and get the rate law that you wanted. I expect midterm, you guys should be able to work on the problem like this. So next we'll talk about catalysis. Most of you already know catalysis can lower the activation and energy. But however, you have to recognize that this is the terrible drawing here. Catalytic reaction, the heat of a product formation would not change. It only change your activation energy, okay? So for enzyme, when we talk about enzymatic catalysis, it's a biomolecule that stabilizes your transition state, which in turn make this reaction process progress much easier because you have lower energy barrier, okay? So in some cases, for example, on page 728, if you look at figure 16.23, there are going to be some intermediate that show up in the reaction, right? So then it's possible that you will not get a smooth shift of your transition state. You may have multiple transition state. In some extreme cases, you may have 5 or 6 transition state. But does it matter? I mean, it really depends on what kind of scientist you are, okay? If you're doing catalysis, if you're trying to understand how things happen, then it probably matters, right? So 2 important concepts in catalysis is that there are 2 types of systems. Homogeneous catalysis, that means your catalyst is perfectly soluble in your reaction mixture. And also the process that is heterogeneous catalysis. So you can think about, you guys probably already seen the YouTube video where they put a piece of Mentos into Coke and cause the release of CO2, right? So that is a perfect example of heterogeneous catalysis because the microstructure surface accelerate nucleation of CO2 bubbles and cause the release, lower the release barrier, energy barrier of CO2 from the solution, so the Coke will shoot out. And here is a series of important industrially relevant heterogeneous catalysis process. So last semester, you guys read about Haber. The Haber process, it's impossible today to replace this process. It generates ammonia, which is an important feedstock for a lot of chemical reaction. It basically allows us to capture nitrogen from the atmosphere and convert it into a bioaccessible reagent, okay? So then, for example, plant can utilize the nitrogen because for gaseous nitrogen, when nitrogen is a gas, the plant cannot consume it very effectively, okay? We breathe in a lot of nitrogen, but we basically just breathe it out, okay? We cannot really react with it. But this high energy process, it's a high energy, high pressure process, force nitrogen and hydrogen collide into each other with the help of these catalysts, okay? So they go through stepwise process such that nitrogen and hydrogen will absorb onto these catalysts, form some sort of bonding with these metal, okay? And then they will, then reaction happens, okay? Without these catalysts, such a reaction would not happen, okay? Then we can look at this process with vanadium oxide or platinum, okay? We can oxidize SO2, okay? We can obtain SO2 by burning sulfur. Why is SO3 important? We can dissolve SO3 in sulfuric acid, right? H2SO4. And with the presence of water, you can make sulfuric acid in this process. And we mentioned Ostwald. Why is Ostwald important? Okay, he figured out a way to convert ammonia in, I think this is a reversible reaction. He figured out an alternative way to generate ammonia and nitrogen oxide. Okay, so if you read your chapter 14, there's a lot of reaction that's describing what's going on. And finally, steam reforming reaction is the water shift reaction, okay? We can convert methane into hydrogen, okay? And we can, there's an efficient process to separate carbon monoxide from the hydrogen, then we get a fuel. And I skipped this, the water gas shift is where we can convert carbon monoxide into hydrogen, okay? So these two processes are very important because now we already have the technology for hydrogen fueled car. For example, in California, in fact, I actually ride in one of the Uber, right? And it was on a hydrogen fueled Toyota. The only drawback is that you cannot have hydrogen station within the city because it's a safety hazard, okay? So the taxi driver have to drive 20 miles, which is about 40 to 50 kilometers outside of their home, okay, outside the city to go to the middle of nowhere to get nitrogen, to get their car refueled with hydrogen. All right, so because people want methanol, right? So the methanol synthesis is from CO, so it's from an incomplete combustion of carbon. You generate some carbon monoxide, and in the presence of catalysts, you can simply convert CO to methanol, right? So why would you care about rate law? Okay, so chemical engineer look at different conditions they use. That is pressure, right? That is the amount of catalyst they use, and that is the flow rate, and to determine how far they want to push a reaction. Because if you can push a reaction to this part, to your product, then you don't have to worry about separation, but that is only the ideal case. And also catalytic hydrogenation. Okay, so this in organic chemistry, you will see that over and over, that convert double bond into single bond. Okay, why is that important? So in fatty acid, in oil, there's a lot of double bond, and that causes a foul smell due to oxidation of these double bonds. Okay, so if you can remove these double bonds, you can make the oil more stable. So that's all I have for this. And the next class, we will have a demonstration that illustrates the effective temperature and the reaction rate. And that reaction is also related to equilibrium. And we will briefly mention what I think is important in chapter 14. And then we will move on to chapter 17.